Hello everyone, Dr. M here, here to explain the ChiSquare test. This is within the context of a genetics lecture, but it's really applicable to any type of data. So, ChiSquare, I just want to say here that it's the ChiSquare test and not the Chi-squared test. Chi it looks like an X, it's a Greek letter, and the square, the Chi-square is the statistic. So you don't have to square your answer. Don't do that. Just take it as it is. It's the name. It's the name of it. And you don't have to do anything to it other than just, calculate the value and go from there and generate your conclusions. So how do we do that? All right, so because this is a genetics class, we're placing it in the context of figuring out whether or not your certain cross might follow Mendelian principles. And so I talked about Mendelian principles and how to use them to follow laws of probability and to be able to generate expected phenotypic proportions from any given cross. And so to get caught up in that, check out my two previous videos on Mendelian principles and probability. All right, so let's say we have a cross between these two individuals. These happen to be pea plants, and we have generated, using Mendelian principles and laws of probability, we have generated these expected probabilities or proportions. Just a key here, when I talk about probabilities, I will often be talking about them in the context of decimals. In this case, because of the nature of the math here, it was easier to express them in terms of a fraction. Same thing, fractions can be expressed as decimals, so don't get confused on those points. All right, so from these expected probabilities, how do we calculate what our expected data in terms of count? So, in order to do that, we are going to say, take the total number of seeds or progeny that resulted from the cross, and that's our total, and we're going to calculate how many seeds we would expect of this total for each of our phenotypes given the probabilities that we calculated, which are these. So these are our probabilities, and remember also that you can have probabilities that are expressed as a fraction or as a decimal, same thing. And from these probabilities, all we do is to multiply each of them by the total number of 542 seeds to get our expected counts. Okay? So now that we have our expected counts, which are these are now our expected data. Now, when we actually run this experiment and count the categories, the phenotypic categories into which our 542 seeds actually fall, say we get this data set. Now, what we want to know is, are the actual data that we get significantly different from our expected data? That is, are these two data sets statistically significantly different? It should say statistically significantly different down here, but okay, so moving on. So in order to determine that, we use hypothesis testing. And what this does is it's an approach to science using the scientific method that allows us to test hypotheses and to determine if our observed results deviate significantly from what we expect. And it places it within the context that alternatively, so we have a hypothesis and then we have an alternative that says, an alternative possibility is that we could have gotten the results that we observed strictly based on chance alone. So if we have a strong significant difference, that indicates that it's less probable that our hypothesis is not supported. We were incorrect, but we're being fooled by our data, and actually There's nothing really interesting going on here. It's just that we happened to get unlucky and got these amazing data, and it looks like they're statistically significantly different, but biologically there's nothing going on. So the probability of getting these results based on chance alone in that case would be very small, in which case we would have stronger support for accepting our hypothesis that our results do in fact deviate significantly from what we expect. Okay, so when we're actually putting this into action, we're going to start out with a hypothesis, and in this case we're going to hypothesize that our cross follows Mendelian principles of segregation and independent assortment. Therefore, our expected data do not differ significantly from our observed data. Okay, so we want these two data sets to be more or less the same statistically. Alternatively, our null hypothesis is just the opposite of that our cross does not follow Mendelian principles, and therefore our expected data do differ significantly from our observed data. So this is what we're testing. And to do this, we are going to use the ChiSquare test. So this is our ChiSquare goodness of fit test, and it's testing if our observed results differ significantly from our expected. And this test is especially appropriate for data that are counts, when you're counting numbers of observations in different categories. And this is the formula that we use. And so what this looks like is, let's say we have a handy-dandy table of our categories and our number of observed counts in each of our categories, as well as the number that we expected to find given our hypothesis. So we plug those into the equation. We're going to do observed minus expected squared divided by expected, and then add those across the different categories. And our total chi-squared value is 2.96. All right, so whether or not this 2.96 is statistically significant, which would indicate that there is a significant difference between observed and expected, that depends on the degrees of freedom. And for a chi-square test, usually you're going to calculate your degrees of freedom as n minus 1, where n is the number of categories. So here we have 4 categories, so our degrees of freedom is going to be 3. All right, so now we have our degrees of freedom, we have our chi-square. Now we have to look up this value on the chi-square table. So a little bit on how to actually read a chi-square table. So up on the top are the p-values, possible p-values, and then below them are associated chi-square values. This 0.05 column is highlighted because it is our boundary between not significant on the one hand and significant on the other hand. So if you have chi-square values that are less than these 0.05 values, you do have a significant difference. If you have chi-square values greater, let me rephrase that. If you have chi-square values that are greater than the chi-square values in this column, you have significant difference between your two data sets, your observed and your expected. If you have chi-square values less than the values in this column, you tend to have not significantly different observed and expected data sets. Okay, so for us, again, here our chi-square is 2.96 and our degrees of freedom is 3, so we're going to look in this third column that's associated with degrees of freedom 3, and we're going to see that, okay, our value falls in between 0.1 and 0.5 p-value. So we can conclude that our results are not significantly different from expected, and this supports our hypothesis that our observed equals our expected, that is, our cross does actually follow Mendelian principles. I want to point out here for my students that if I were to give you this on an exam, I would expect to see your chi-square value, of course. I would expect to see a p-value. I would expect to see your conclusion, and I expect to see your degrees of freedom. Okay, so there are a number of components that are necessary to accurately report a chi-square test, the results of a chi-square test. Now, in reporting p-values, because our chi-square table is not completely accurate, you're obviously going to find usually your chi-square value falling somewhere in between different categories. So when reporting p-values, I want you to, if it's not significantly different, it is okay just to say greater than 0.05. That's fine. However, if it is significantly different, I'm going to want you to say less than whatever the greater p-value is that you found. So if you have a chi-square that falls between 0.025 and 0.01 in here, then I want you to say that it's less than 0.025. If it falls here, I want you to say it's less than 0.05. Okay? So that is the chi-square test.